Welcome everybody to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla, and this is a series of videos in which we show students how to set up and solve introductory physics problems. Today we're taking a look at scales of temperature. So, for a variety of historical reasons, temperature as measured has come down to us primarily in three basic units. It depends pretty much on where you live or what your job occupation is as to what temperature scale you use. So in the United States, still kind of a holdover for most of the world, we use what's called the Fahrenheit scale. You're familiar with that as 32 degrees Fahrenheit is the freezing point of water, and 212 degrees Fahrenheit is the boiling point of water. So water is the basis of the temperature scale. A good way to remember why it's the numbers that they are, now I don't know why 32 specifically, but 212 minus 32 is 180, which is in degrees the opposite side of a circle, and maybe that's what Fahrenheit was going for when he decided to set it up this way. So who knows? I'll have to ask Fahrenheit the next time I see him. The other unit of temperature that's commonly used around the world is Celsius, or sometimes referred to as centigrade. Celsius makes it a little bit simpler in that 0 degrees is the freezing point of water and 100 degrees is the boiling point of water. And again, they're kind of opposites, but Celsius himself decided to make the number a lot easier for us all to handle. And that's what's used in most of the world. And then there's the scientists, like yours truly here. We use Kelvins, or Kelvin, as opposed to Kelvins. It's usually just Kelvin without the S attached to it. Kelvin is useful for scientists because it's an absolute temperature scale. Celsius and Fahrenheit are both relative temperature scales. Even though we call it 0 degrees for, say, the freezing point of water for Celsius, that's not the coldest possible temperature, right? You can get colder than freezing of water. In fact, you can get a lot colder than that. And of course, you can get colder than 32 degrees Fahrenheit. So Kelvin was an attempt by Lord Kelvin back in the late 1800s to set a temperature scale where 0 meant 0, that there is no temperature, that there's no energy available for this kind of thing. Now, there is a law of thermodynamics that says you cannot actually ever get exactly to 0 Kelvin. There's no such thing as getting to absolute 0 in any finite lifetime that you or I will ever experience, but that's perhaps a topic for some other video. In this case, we just simply know that, at least in theory, 0 Kelvin means there's not a temperature. Why is that important? Because when we go to other places, when we calculate with temperature in anything but the simplest of fashions, we want to know the actual absolute number as opposed to relative numbers. So Kelvin has its uses. But we're not here to worry about that too much today. What we're worried about is showing how to convert between the different kinds of units. And so these three formulae here are just different methods for converting units. So units of Fahrenheit degrees, Celsius degrees, and Kelvins. Now, by the way, this reason it's called degrees Fahrenheit and degrees Celsius is because they are relative measurements. They're relative to the freezing point of water. Whereas Kelvin is an absolute temperature scale, and therefore it's not degrees Kelvin. Notice there's no degree symbol on the K. All right, so let's do our first one here. Let's try it out when the temperature is 20 Celsius. So the temperature is 20 degrees Celsius. What is that in Fahrenheit and Kelvin? Now, why choose 20, by the way, very quickly? It's what we call the standard temperature chosen by a lot of scientists around the globe. As you'll see, especially if you're in the United States and you're not familiar with what 20 Celsius means, it's more or less an average temperature for the planet. Not exactly, but close enough. And it's a simple number to work with, at least in Celsius terms. And it's also not freezing because not all of us live in freezing temperatures. So let's go ahead and do that calculation for Fahrenheit first. So temperature expressed in degrees Fahrenheit is equal to 9/5 multiplied by the temperature expressed in degrees Celsius, then add the number 32 to that. Okay. Now in this case, don't need to worry about writing degrees Celsius here. This is not a conversion in a traditional sense in any case. So let's go ahead and do this. 20 divided by 5 is 4. And so we have, say, 9 times 4, if I want to write this out to make it obvious what's going on. 9 times 4 is 36. Notice we're adding the 32. Why are we adding the 32? Because this Fahrenheit scale is or the freezing point of water is at 32, isn't it? That's why it's there. And 36 plus 32 is 68. So if someone from some other country tells you that the temperature was a nice, really beautiful day at 20 degrees Celsius, that's 68 degrees Fahrenheit. And that does sound like kind of a nice, simple day outside. All right, how about the Kelvin scale? Kelvin's a much easier calculation. It's just an addition if you have the Celsius number. So we're going to round off to add this. There's usually like a 0.16 or therefore after it, but let's round off for today. So this is just simply 20 plus 273, or 293 Kelvin, like that. Okay. So if you're in a room or if you're outside and the temperature is 68 degrees Fahrenheit, which is the same as 20 degrees Celsius, 293 Kelvin. And that gives us a little bit better perspective, by the way, on what the meaning of the temperature scale is. 293 sounds like it's kind of warm. It means that there's a lot of degrees to go to get to zero, right? Or a lot of steps, if you will, to get to zero. So it's a little more obvious about that in the Kelvin scale. It's another reason to talk about it. All right, what if we start with the Kelvin scale of 300? So in a lot of simple math problems, physics problems, often people will start with 300 Kelvin rather than, say, 293, because it's a real simple number. But does that mean it's a simple number for these other units? Let's take a look. So my temperature is 300 Kelvin. Now, the way to get to Fahrenheit is to first go to Celsius. So let's do that. So temperature in Celsius will be the temperature in Kelvin minus 273, right? So 300 minus 273 is 27 degrees Celsius. Like that. So fair enough there. All right. Next question is then, what is it in Fahrenheit? So temperature in Fahrenheit is then, again, 9/5 temperature in Celsius plus 32. 9/5 multiplied by 27 now, plus 32. And to shorten this up a little bit, I'll round off and just give you the number at the end. You can double check my work. 81 degrees Fahrenheit. Notice, by the way, it didn't take much of a change of Celsius to have a bigger change in Fahrenheit, which is to say that each step, if you will, each going of 1 degree to the next in the Celsius scale, is almost twice as big, 9/5, as the equivalent steps in Fahrenheit. So it's a big jump. It's, to go from, say, you go only 7 degrees in Celsius, you've gone 13 degrees here in Fahrenheit, roughly, right? Now, last one I wanted to show off was a bit of a, I'd say urban legend, perhaps. And that's the supposedly standard human temperature, that you're supposed to have ideally a body temperature of 98.6 degrees Fahrenheit. I'm here to tell you, not quite, for a couple of reasons. One is there is no such thing for an exact number. Humans all have slightly different situations. They're different ages, different body chemistries. They're all sorts of different medical histories. And so a temperature that I should have might not be exactly what the temperature you should have anyway. So that's a misnomer to start with. But it turns out it's even a physics or math misnomer, and here's why. So let's suppose we go ahead and convert the temperature in Fahrenheit to the temperature in Celsius, and I'll show you what happens. So temperature in Celsius is 5/9 multiplied by this calculation, temperature in Fahrenheit minus 32, like that. Okay, so let's take our 5/9. Then we have temperature in Fahrenheit was this 98.6 minus 32, like this. All right, 5/9 and 98.6 minus 32 is 66.6. That sounds kind of ominous. It isn't ominous at all. If I do this calculation further, I get this as my answer, 37 degrees Celsius. And this brings a bit of a problem, if you will, or what I've actually done is I've shown it in the opposite direction of what it actually happened. So when doctors were first trying to figure out how temperature worked for people, one of the more common results they were getting for healthy people was around 37 degrees Celsius. Again, they're working that temperature scale. For whatever reason, one of those historical things, it's like being told you only use 10% of your brain. That's not true at all. It has nothing to do with that. You use all of your brain all the time. I'm sorry to tell you that, everybody. Similar sort of, kind of urban legend type of propagation here. The 37 degrees, if you calculate it, can be shown to be 98.6 in Fahrenheit, as you can see here. But that ignores significant figures. One of the things that you know by now, significant figures matter. And now when we do our videos here, we often kind of skirt that a little bit just to demonstrate, but this is worth the discussion. 98.6 is assuming you have an extra significant figure you didn't have when you talked about 37 degrees Celsius, right? 37 has 2 sig figs, 98.6 has 3. On top of that, the Fahrenheit scale, as we already talked about, is even more sensitive than the Celsius scale. So it's even worse than that. You're claiming, in other words, a lot more sensitivity, a lot more precision to the number than actually exists. It would be far more proper to say that the average human temperature should be roughly 99 degrees Fahrenheit. Or better yet, range from about 98 to 100 degrees Fahrenheit. And if you're in that range, you're in good shape, by and large. So that's a small, interesting little side tidbit about temperature scales. Anyway, this has been showing how to convert between temperature scales. I hope this comes in useful. Technical support is from Sidney Gauchow and Sophia Turner. Our funding comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Sorolla. Thank you, everybody, for your attention, and clear skies.